Greetings, this is Charles Darwin, and I'm going to tell you today about the scientific method. And one of the most important parts of the scientific method is to have an adequate control for your experimental treatment. And this isn't always as easy as you might suppose. Now, we were worried about this in my day when I was alive doing experiments, but there's been, since I died, there's been quite a bit of progress in scientists coming up with proper controls for their studies. One of the most famous examples within the last 10 years was a 2006 article published in Science by Matthias Wittlinger and Associates, and they were testing the hypothesis regarding how ants find their way back home. You see, if ants are out foraging at random, and then one of the ants finds some food, what he's going to do is take a bite of the food and go straight back to the nest so that the other ants can follow his scent trail and get to the food also. But how does the ant, when it's returning home, know how far to go? Their hypothesis was that the ants integrated the number of steps. Now, the ants couldn't actually count the number of steps, but they integrated the number of steps. And what this meant is that if an ant had shorter legs, and therefore took shorter steps, it would not go back far enough to reach the nest. On the other hand, if it had longer legs and took longer steps, it would go too far. So these were the two hypotheses, and they wanted to test these hypotheses. So how do you think they did that? Well, you might think, well, take two different species of ants, or three different species of ants. Short legs, medium legs, long legs. However, species of ants differ from one another in a lot more than just the length of their legs. So what they had to do was take ants of the same age, same caste, from the same colony of the same species. And in that case, how would they produce ants with short legs and ants with long legs? Well, the way they did that was, let me check here. The way they got ants with short legs is they broke the end segments of the legs off, thus creating ants with stumps. Now that may sound cruel, but their tests showed that the ants, once the stumps had been broken, were able to walk just as fast, not exhibiting any signs of pain. I suppose that's a comfort to us. Now, how did they get the ants with stilts? Well, they glued pig bristles onto the ends of the legs. And so these ants took longer steps. So the article was entitled, "The Ant Odometer Stepping on Stilts and Stumps." And it was a very famous article read by a lot of people who were not otherwise interested in ants or in any other kind of insect. Now, this was a very interesting example of an experimental control that was suitable for the treatments. Also, it seems that scientists like to torture insects and have the same about superglue. Well, let's see what else happens. Here is an article that was published in 2012. The lead author was Dror Helena, and what he wanted to do was to show that when grasshoppers are frightened by spiders, the fright is so strong that it will cause the feces of the grasshoppers to have more carbon and less nitrogen in it. And that this effect was so strong that it would actually slow down the decomposition of the litter. So what they did was, you would think, they would just have the grasshoppers with spiders, the grasshoppers without spiders, and see which one had grass that decomposed more rapidly. You would expect the grass where you had the grasshoppers with the spiders to decompose more slowly to test that hypothesis. However, if you have the spider and the spider will attack the grasshopper. And what they were wanting to find out about was, does the fear of spiders, not just the presence of spiders, alter the decomposition rate? So what these authors did was they glued the spider mouth parts shut with superglue. What is it? These scientists torturing insects, and they just love superglue. What's going on here? Well, let's try another example. Here's an article that was published in 2012 by Shohat Ophir and Associates. And what they wanted to show was that sexual deprivation caused male fruit flies to crave alcohol. Now, you may recognize this as being something that male humans may do also. That when male humans are rejected by females, they'll go to the bar and drink. But do fruit flies do this? Why would anybody want to know? Well, if fruit flies do it also, it shows that the hormonal and physiological basis of this behavior goes back to a common ancestor of both insects and humans, which would have lived several hundred million years ago. And so what they had to do was have male fruit flies that had had the satisfaction of mating, and male fruit flies that had not been able to mate. Now you might think that would be very easy, just have males that have mated and those that have not. However, the males that have not mated are physiologically different from the ones who have, not just in their experience of sexual deprivation, but in lots of other ways too. So the way these researchers wanted to produce sexually deprived males, sexually frustrated male fruit flies, was to expose them to females that would not mate with them. Aha! Here it gets complicated because when a female rejects a male fruit fly, the process of rejection may be different than simply the process of not mating. So what these researchers had to do was to somehow expose the male fruit flies to female fruit flies that would neither mate with them nor reject them. And yet that's the only two things that female fruit flies ever do, is they either reject the males or they mate with them. So the way that they were able to produce the appropriate experimental conditions was, let me read this here. They used decapitated female fruit flies. This is just getting worse and worse. Scientists using superglue and torturing insects. Okay, certainly you would expect they do not do this with mammals, right? Well, in the article immediately after the one by Whitlinger about ants, stilts, and stumps, there's an article called Social Modulation of Pain as Evidence for Empathy in Mice. And what they showed is that if one mouse is writhing in pain and another mouse is observing it, the observer mouse will also writhe in pain. Now, this, however, does not prove empathy. There's two possible explanations. One is that the observer mouse feels sorry for, feels empathy for the mouse that is suffering. Or it could simply mean that the mouse, the observer mouse, is frightened that the same thing might happen to him. So, what do? What these researchers did was they compared observer mice that had been raised as litter mates with the suffering mouse, and therefore might expect to have more empathy for it, see if they wriggled and writhed more than mice, observer mice, who had not been raised as litter mates with the suffering mice. And as a matter of fact, they did find that mice that had been raised as litter mates were more likely to wriggle and writhe in response to watching a litter mate suffer than a mouse that they had never met suffer. Okay, you may wonder, how do they get the mice to wriggle and writhe in pain? They poked them with needles that had acetic acid, vinegar in it. Is there nothing that these scientists won't do in order to test a hypothesis? Well, I tell you, when I was alive, and I did experiments, I didn't torture any insects or any mammals. Of course, maybe sometimes that has to be done in the name of science. I will leave that for you to decide. Meanwhile, this is Charles Darwin. Tally-ho, and amen.